Welcome everyone to another math club talk. Today we have with us Advait Sunder. He is from B.Math third year and he is primarily interested in low-dimensional topology, and he will be speaking on the fundamental theorem of algebra and he will be proving it using the complex analysis. Over to you.
Thank you. Hi everyone. So as you can see, I'll be proving the fundamental theorem of algebra largely via complex analytic techniques. This talk is meant to be expository, so feel free to interrupt if you have any doubts with regards to definitions, arguments, notes. So, first I'll just give a rough overview of how the talk is going to go. I'll first introduce the notion of a holomorphic function. Secondly, we'll see a little bit of what power series are and some properties with respect to their differentiation, integration, so on and so forth. Next, we'll show that any holomorphic function can be given as a power series. So we'll see the power series representation of holomorphic functions. And finally, we'll prove Liouville theorem. And from that, we'll conclude fundamental theorem of algebra. Right? So, let's start. Start with the notion of a holomorphic function. So, you guys know what differentiability means for a function defined on some open interval to R. We want to extend this notion to what a function means, what it means for a function to be differentiable on C. So here we choose this domain very smartly because for any point in the domain, we want to be able to move in all directions freely. So we want to replicate this when we choose our domains in C. Basically, if you're on the complex plane and you choose a line, you don't have the freedom to move in each direction. You want this freedom because you want to be able to differentiate, which means given your change in your input variable in any direction, you want to be able to characterize when a function changes. So for this, you need to allow your input variable to vary in each possible direction. So your obvious candidate for this will be what are known as open balls, which on the complex plane are defined by, so for an open ball, you need to have a center and a particular radius around that center, which we denote by a ball of center P and radius R to be the set of complex numbers which are at distance R from P. Right? And we generalize this to define an open set in C. To be a subset of C such that for any point in your subset, there will be some positive radius such that the ball of radius R centered at P lies in. So we will use this as our domain for where we want to define differentiable functions. So, alright. Now that we've got that out of there, we'll see what exactly we mean when we say the function is differentiable. Suppose you have a function from some open set to C. We say that f is differentiable at some point z0 in U if the following limit exists, which we denote by f times z, not in C. This is what we mean when we say a complex function is differentiable. Right? Now, extrapolating from what we know in functions of a real variable, we can see that, obviously the identity function is differentiable with its derivative being 1 at all points. Right? Secondly, we note that for f and g, defined on the same open domain to C such that both f and g are differentiable at z0. We note that any linear combination of f and g is differentiable in the same domain, and its derivative will, of course, as we expect it to be given by right. Secondly, fg will also be differentiable, and its derivative will be again what we expect from a single variable calculus. And finally, if g of z is not equal to 0, 1 over g is differentiable, and its derivative, as you would expect, would be and yeah, now we can define what photomorphicity means. F is said to be photomorphic on a domain U if f is differentiable at z for all z. Alright? So yeah, that's the definition of photomorphic functions. And yeah, now we can take into the second part, that's the power series. Alright. So power series. So these power series are very special types of functions, which special in the sense that they are infinitely differentiable. Meaning you can take a derivative, you can take the derivative of a derivative, so on and so forth. So we define it to be some function that takes z to sum in z minus a of n, where n belongs to C, a belongs to C, obviously this is for all n. And yeah, so obviously we are not interested in when this function goes to is unbounded or divergent. We want to see when this is convergent, and that's the only place we want to focus on studying this function. Turns out, for nice enough an, the set on which this is convergent is an open set, and in fact, so okay, first we'll see one general lemma. It says that if this can be bounded by some r power n for some fixed r in r less than 1, then we automatically know from whatever sequence series you guys have done in your left and with that this obviously converges to 1 minus r, and by comparing this with this, we can say that so does this converge. And we are primarily interested in studying this, or rather when this converges, right? So, assuming the function so assuming this function converges everywhere in U, I shall make some claims. They are not very hard to prove. Proving them would digress from the path of this talk, so I'll just state those claims. First of all, f is continuous on U. Secondly, f is differentiable, as I said. In fact, these are infinitely differentiable functions. And this is just the derivative you'd expect it to be. Thirdly, so you note that even this is differentiable if it is well defined, and this is an important claim that wherever f converges, f prime will also converge. Inductively, we can say that wherever f converges, the gauge derivative of f will also converge. And finally, so f is supposed to be said to be uniformly convergent on U, and whenever you have some, so So might as well mention this with uniformity converges U, and whenever this happens, you can always differentiate, and you can also integrate to give again what you would expect. So that's the bit about power series. One last bit. So we know that f is differentiable, we know it's infinitely differentiable. In fact, we have a very good equation or relation between the derivatives of f and these coefficients given by so yeah, this is but yeah, this is what we have for power series, and I think that gets all the required diagram out of the way, and you can now proceed to the most important part, that is the power series representations of holomorphic functions. Alright, so what we want to show by the end of this section is that any holomorphic function can be given as some power series. You should note this is a very strong result because holomorphicity just guarantees f is differentiable at some point or in a neighborhood. That is, the neighborhood is just an open set. So from that, we just from knowing it is differentiable in some neighborhood, we can say it is not only infinitely differentiable, but it actually has a power series representation. And before that, I'd like to state one technical lemma, which is not too hard to see. Again, proving this would digress unnecessarily, so we shall just state this. Suppose you have some function, two real variables, A to C, given by g of s t. Then you can define f of t Note over here t is fixed. When you want to evaluate f at t, you are just varying s and then you are integrating over s. So automatically the lemma I want to state is that first of all f is continuous, and secondly if we assume del g by del t is continuously differentiable, it's just continuous, in this case is continuous, then you can define df by dt, which is the integral of del g by dt. Okay, awesome. So you can try proving this on your own. It's not too hard. It's just some computations that need to be done. And using this very crucial lemma, we will show that all power series can be, all holomorphic functions can be represented as power series. So before we get into that, there's one more notion I'd like to define, that is the integral of a function over a path. For the purpose purposes of this talk, you just assume a path to be some smooth function from 0, 1 to c, such that d gamma by dt is defined as 0. And in fact, is also continuous. Alright? And given, so I shall note its range as this with a very temporary notation, and we will see that for a function defined on an open set such that the open set contains the range of gamma, we define the notion of the path integral of f over this curve to be f evaluated at gamma of t times the time derivative of gamma as t goes from 0 to 1. Right. So stating all this, you can prove the first result of the talk. Which is that you have this integral there. So the integral of this quantity from 0 to 2 pi, as theta ranges from 0 to 2 pi, will always be 2 pi for any z you take in the open ball of radius 1 around 0. This might be very scary looking, but this just says that given some motivation, you just take e power I theta 0 to 2 pi, as theta goes from 0 to 2 pi, is nothing but the unit circle, right? So given any point z inside this, it just says that the total angle covered with respect to z as you traverse through this whole path is exactly 2 pi, which is what we'd expect it to be, right? You make one full circle, you go 2 pi radians. And so, okay, we should prove this lemma with a technique that's going to be used at least 2 more times in this talk. I should show that this, so I shall, so assume instead of z, you had it at 0, right? Assume z was 0. So you put 0 over here, these two would just cancel out to be 1, you just integrate d theta from 0 to 2 pi, you would get 2 pi. So this result very trivially holds for when z is 0. So for any other z, this is the most important notion in this talk. Just an idea, I don't think proving it would be very useful. That if you can continuously deform this curve to go to some other curve, or rather smoothly deform this curve to go to some other curve, you will get the integral should still remain the same, right? So what we want to do is, so by taking z equal to 0, we showed that the integral from 0 to 2 pi is 2 pi. Rather, we can say that for any ball, or rather if we take gamma of theta to be w plus e power I theta, we can say that the integral so basically the integral of theta minus w gamma d theta will always be 2 pi, right? This just again says that you just go around the circle and the total angle you get is 2 pi. And now what we'll do is we shall take this circle that is centered at 0 and continuously deform it to a circle that is centered at z. and then we get a result, because the integrals over this curve and any other curve is smoothly deformed to must be the same. This notion is that of a closed form in differential geometry. You might see this later, but yeah, for now just accept it, because it's a very intuitive idea, right? Just if you're able to take the curve, it's a closed curve, and if you're able to take it from one place to another, because it is closed, you shouldn't have any issues with the total value of the integral. So, right. So now, okay. So one way of doing this would be to taking this curve and continuously deforming it to a curve whose center is z. This is 0. This is 0. But instead of that, because that seems a little tedious, what we do is we take z and we continuously deform that to go to 0. So we shall now define phi of theta comma t. Yeah, we defined on 0 to y cross 0 comma 1 to c phi of theta comma t to the e power by theta, e power by theta. So at t equal to 0, we see that this is exactly nothing but the circle and z is nothing but 0. At t equal to 1, this is exactly what we want to integrate. And by showing that the integral of phi theta comma t with respect to theta doesn't vary as you change t, you'll be done. So now we define g of t to be 0 to 2pi e power by theta, e power by theta minus dz d theta. Right? So we eventually want to show that g of 1 equal to g of 0. How we'll do this? We shall differentiate g by that lemma we proved over there and show that its derivative is always 0. But before that, something I forgot to mention here, if you have a function f such that its derivative is small f, then our integral of gamma of f, which is nothing but f prime gamma of t, gamma prime t, as t goes from 0 to 1, t is nothing but and as you guys know from Fundamental Theorem of Calculus, something done in 12th is nothing but f of gamma at 1 minus f with gamma of 0. Right? Keeping this result in mind, we should differentiate g and show that its integral is, its derivative is 0. So g prime t, as we know, is 0 to pi del by del t theta, theta minus dz theta, which is 0 to pi z e power by theta, e power by theta minus dz whole square. Right? And now we want to show this is 0. How do we do that? We can say, okay, if there exists some phi from 0 to 2 pi for the fixed t to c, such that phi t prime or its theta derivative is exactly equal to this. And some constant say, then we can just substitute this over here. We get phi of phi t at 2 pi minus phi t at 0. But since your theta is an angle variable over here, we see that phi t evaluated at 0 and phi t evaluated at 2 pi is the same. So we should get that this is 0. The integral of this is 0. So now it just boils down to choosing what phi t is. So we choose, I missed a minus over here, sorry about that. So yeah, we choose phi t of theta zi or e power I theta minus dz. So what is phi t prime theta zi and this is exactly later, and this is exactly z e power I theta upon e power I theta minus dz whole square. So wonderful, you have found a phi t rather, whose partial with respect to theta is exactly what we want to integrate. So we just use this. We finally get g prime b equals right? Okay, so we know that g's derivative is 0 everywhere for all t, right? So we can easily get that g of 1, okay, if g's derivative is 0 everywhere, then it must be a constant function. So you get g of 1 equal to g of 0, 0 to 2 pi, e power theta minus 0 times z, theta which we already saw was 2 pi. So we get that this integral okay, let's take a pause and see what we have done here. We took this, and by taking one extra variable, we get this as a function of t. We showed that g's derivative is 0 with respect to t by showing that you are just integrating something that is a derivative of something else, right? That is, you are integrating something that is a primitive. As we saw by fundamental theorem of calculus, the integral of a primitive is just the difference of the primitive's value at the two endpoints. At the two endpoints, the function is actually the same because you're considering 0 and 2 pi. So you indeed get that g's derivative is 0 and hence g must be a constant function. As a result, you get that this is always 2 pi. Good. Now we move on to one of the most important formulas in introductory complex analysis, which is that you have a function defined on a ball of radius r plus say 1 to c, such that f is orthomorphic on its domain. Then the integral 0 to 2 pi, or rather gamma, we just define what gamma is in a bit. Take this to be some center A. pi I times f of a, where your gamma So gamma, if I were to draw this, is just you take some center A, you draw some ball of radius r plus 1 around it, open ball, so that it contains the circle of radius r about A inside the domain, so that you can define your function on this. You see that when you integrate over this entire circle, you just get f of a with some factor. This is a very important theorem because by knowing what the values are at this curve, you can fix what the value is at this point. So, yeah, we try doing this. And the motivation remains the same. You want to continuously deform your path to another path and then show that the integral on either of these paths must be the same. So, proof. Right. So, what kind of deformation are you looking for over here, right? So, if this is your point, this is your r radius circle, and this is your gamma, you know that you can continuously deform this to a point, to the point A, right? And at A, this integral is exactly equal to that. Do you see that? So, okay, I'll just show that for those who will do 0 to pi. So you have f of a plus 0 e power I theta, because I'm taking your radius to be 0, times the theta derivative, which is just I e power I theta, times 0 is just okay, you are just integrating at a point. So you are just integrating f of a times some factor I, because that's what you get when you differentiate your curve. This will just be related to this form. I'm sorry. So f of a plus r e power I theta, I r e power I theta upon w minus a, which is again just r e power I theta, right? Because w is a plus r e power I theta minus a again. So you just get r e power I theta. This and this will cancel off. And when you take r to be 0, or when you limit r to be 0, you just get 2 pi I times f of a. So you can see that when r is very small, by continuity of f, that integral for very small r is exactly what you want it to be, or very close to what you want it to be. So we will just use this to get the deformation we want, and then we should prove this lemma as well. So this is what you want to be integrating. So you just look at phi of theta comma d again to be f of a plus 1 minus t r e power I theta, right, times its theta derivative is just 1 minus t I r e power I theta upon the difference of w and a. So you just want this minus a, so you get 1 minus t r e power I theta, and this, as you want it to, will cancel out, and you just get f of a plus 1 minus t r e power I theta times I. Right? Again, we shall integrate this for different t, show that its time derivative is 0. Time derivative, I mean derivative with respect to t, and hence its integral at 0 and 1 for values of 0 and 1 and t must be the same. So we integrate 0 to 2 pi f of a plus 1 minus t r e I theta and I d theta, and we call this g of t. We find what is g prime t. So yeah, this argument will be used a lot. So I hope you guys are comfortable with this. 0 to pi, the time derivative of this. There will be 1 minus t. Will be f of a plus f prime rather, because we're taking the these steps. Here, right? So again, we want to find some phi. So if we call this h for the moment, h of theta with a fixed t. Find a phi such that phi to be prime theta is equal to h. Right? And over here it's slightly easier to guess what it should be. You just take f of a plus 1 minus t r e power by theta. And you differentiate this with respect to theta, you just get 1 minus t f prime of 1 minus t I r e power by theta f of t I r e power by theta f prime of a plus 1 minus t theta. So yeah, so the derivative of this is equal to ht times some constant, which we just call ct for the time, right? It doesn't matter. You can scale the integral how much ever you want. If the integral is 0, but regardless of the scaling, your integral will still be 0. So, or rather, we can take phi t to be I 1 upon I 1 minus t. Theta, and obviously by taking this to the denominator, you can see that its theta derivative will be exactly h. So we again do the same fundamental theorem of calculus argument to show that g prime t is 0 to pi t prime theta, which is just 0. Again, because this is just the difference of phi t at 2 pi and 0, phi t at 2 pi and phi t at 0 are the same, because theta at 2 pi and 0 are the same, it's the same angle, so you get 0. So you get g of 1 equals g of 0, and you initially wanted to evaluate at t, rather, yeah, you want to evaluate this at t equal to 0, which is exactly what that is. So you should equate that to what it is at t equal to 1, which is exactly what this is. So without going through the explicit computation, in the interest of saving time, we just say that gamma will be defined to be f of a times 2 by I. So this is a very crucial piece of information. And in using this and again some kind of deformation of loops, we can make an even stronger statement. So as you saw over here, your gamma actually depends on A, right? Whatever, so suppose you want to find f of A, you will always integrate over the curve that is a circle at the radius r from A. We can do better than that. In fact, we should take the same curve and we can see that it remains the same for, you can take any value of z over here, and instead of taking A in the integral, if you take z, you will get 2 pi I times f of z, which will be our next and last lemma to show that every function can be given as a power series. So all this work has been to build up to this theorem. Suppose you have some domain G in which you have some ball around A of radius r, then for any Z you take here, you can always find an open ball such that it is contained in this bigger open set. This is some very elementary Euclidean geometry, and using that, so you have F from G to C. G is open, and you have B, A comma R, license G, and for any Z, you will easily get that there is some R greater than 0 such that your radius lies in. And in such a case, instead of varying gamma with Z, which is what we want to find the function at, we will take a fixed gamma. And our claim is that right? So doing this, we can for a fixed gamma, we can take no matter what Z you want inside this open ball of radius r around A, and get that the integral should always be 2 pi I times f of z. This is a very important lemma, or rather theorem I should say, and this will very directly give us the fundamental theorem of algebra. So I should get through this. And the idea remains the same. You start with a circle of radius 0 at z, and then you continuously deform it to get this bigger circle, right? And that should showing that this is so this act of deformation, for those who don't know this, is called a homotopy, and you basically want to show that this integral is homotopy invariant. That is, when you even if you transform this part under a nice homotopy, the value of the integral stays the same or is invariant. So, yeah. Show this. I want to show that the value f as this is. Right? So now, okay, we just in the starting we note that you are having to work with too many variables over here. A, R, theta, in some time t, z. So we'll do some kind of normalization to make calculations easy, and we'll just assume that A is 0 and R is 1. So we should be looking at, I think this should be right. And yeah, looking at this instead of f of r, f of z, we can show that we can just assume that A is 0, R is 1. Alright? Yeah, so that should simplify computations a little bit. So equivalently, is enough to show that 0 into pi f of theta I e power by theta and theta minus z is 2 pi I of z. Good. We should again find a continuous deformation that takes this point or a curve around this point of radius 0 to this entire curve, and so again, we define phi of theta comma t, f of z theta minus pc. Yeah. So minus pc theta minus z and equals so another simplification. And we should show, or we can assume that t
Well, I think it will be 1 minus tz times p will be 1.
okay, yeah, I mean that's just a factor of minus, it doesn't really matter. Cool. So p right, and right off the bat we see that t equal to 0 is exactly what we want, right? And okay, bear with me for the moment. I will first explain what we're trying to do here and then I'll do it. If we take t to be 0 or rather t to be 1, we just get f of z e power I theta minus z times this I. We take f of z times I out, all we are left with this. So at t equal to 1, g of t is we already know what this is, right? This is the first lemma we proved. This is exactly equal to 2 pi, and we hence get 2 pi I for z. So all we need to do is show that the derivative of g, time derivative of g, is 0. We're automatically done there. Because g of 0 is what we want. We know that it should be equal to g of 1 if the time derivative is 0. G of 1 is exactly your right hand side. So yeah, showing that the time derivative of g is 1 will do our job for us. Same argument again. G prime t d of f of z plus p is I'm missing some term. I'm sorry. Yeah. Sorry about this. Because right. This is when we get g of 0 to be, rather g of 1 to be just a plus, or in this case f of eta or I theta. Because when you put t equal to 0 over here, c and 0 cancel out, you will get what you want. Sorry about this. And get the I out, it's fine. So, right, what is this? We find that this is f prime minus z plus 1 minus p minus z theta I theta minus z minus z minus theta, which is right, and as usual, you will take, you find some phi t whose derivative is this, and then we are done, right? Okay, so yeah, again over here we have a very obvious candidate for phi. We first look at the derivative and see if any matching needs to be done with regards to constants or not. Yeah, so look at f of z plus 1 minus p theta under z, and we find its theta derivative. We will just get c plus 1 minus p theta under z, yeah, times 1 minus t constant times I by theta. So you already have a I here. The only thing you're missing is a 1 minus t. So find this to be right, and then just by this computation we get that g and p 0 to pi theta theta, which get to be 0. Again, because phi is a function of theta, theta 2 pi, theta of 0 is the same, we get g of 1 to g of 0. Evaluating at 1 and 0, we see that 0 to 2 pi f of theta minus z is that 2 pi r. And so this proves the theorem we are wanting to prove, and from this we can very easily get a power series expansion of this, because if you see this as a function of theta must be, this is a function of z must be infinitely differentiable. We'll come to that in a moment as to why that is, but yeah, this should give you a good inkling to why this gives you a power series representation. So, yeah, we can now finally prove that every holomorphic function has a local power series representation. But what I mean by local is in a small ball of radius, whatever that is contained in your domain, you can always express your holomorphic function as a power series. So before that, one small computational trick to see that 1 upon w minus c. So we want to be integrating f of w times w minus c, right? So we can write this as before that, we come over here, we see that by taking fixed z, we can find the derivative, the second derivative, the third derivative, so on and so forth, by just differentiating this. Right? This is exactly what we use there. W minus a, w minus a, 1 minus sorry. This you should be able to recognize as the limit of the sum over GP. Right? This sum is exactly equal to this. This is calculus standard sequence in series. So yeah, and we see that if this quantity is smaller than 1, this will always converge, right? So this integrated as a function of w for a fixed z over any path must converge to this integrated over w, integrated as a function of w over a fixed path, right? We saw by defining whatever the uniform convergence was that you integrate this and you integrate this, you should get the same thing. So this, which is exactly equal to pi of z, right? So basically we want to define some nice region in which this converges so that we can equate this and eventually get a power series representation of f. And you note that for a fixed gamma and a fixed a, this is always constant. These are just for each different time you get just a different number over here, right? This is not a function of z nothing. It's just if you take this as an, this is the summation an z minus a power n. So we should try to find some nice domain in which this converges, and then we have found a power series representation of a holomorphic function. So, I mean, it's enough to yeah. So, no matter what open set you take, you'll always find an open ball. So, as long as you can say this converges in some open ball, you can always find an open ball in the open set by taking a smaller radius to show that this will always converge in that open ball in that bigger open set. So it is enough to define your domain to be an open ball of radius r, right? And for every, and for A, you have that not only is the ball of radius r, but also the circle this thing is also a subset of the bigger open ball, right? Again, it's just very simple Euclidean geometry. It's very vivid. So so this gives us a candidate for what our gamma should be, right? It should just be this circle. So, and on this circle, if I have right? If I have z minus a less than this for all z, in fact, you do actually have this, right? Because if you take gamma theta to be a plus r e power by theta and z to belong to ball of radius small r around a, this will always be less than this because this is exactly r, right? So you obviously have this. So you then automatically get that this converges, right? So now we can make this equality and and then we are done. We've found a power series representation of a holomorphic function. Right. So this automatically gives us size f of z upon y right? This should be clear, right? Okay. So we get a power series representation for a holomorphic function in some open ball in your domain. So instead of this, if I took f g to c, and g contains the ball, you're still fine. You can still take some r less than capital R, some z in this ball, and then this should still work. So it's not functioning. Right? So this is a very good stage to be in because this gives us a very important theorem in complex analysis called Liouville's theorem, which says that if you have a function, holomorphic function whose domain is the entirety of a complex plane, and it is bounded in the whole plane, it must be the constant function. Therefore, any non-constant function must get as large as you want it to get, or arbitrarily large. So this now. Just 5-10 minutes more and we'll be able to see the fundamental theorem of algebra. So this theorem, if f c is the holomorphic on C is bounded that is there is some positive number m such that the constant function. Okay, how do we prove this? Right? We very immediately note that if f is holomorphic everywhere, then f restricted to is holomorphic for all r greater than 0. Right? You can take this r to be as large as you want, and you're still in a good position to say that it is holomorphic. So as we saw, there is a relation between the derivative of a function at a, which is the center of its power series, and its coefficient, right? So we get f prime a to be w minus a square, which is equal to 0 to pi of a plus then you can automatically get a bound on this, known a bound on this. This is bounded by m. But right? Does this make sense? That you can take any small r less than capital R, this will always hold, so this bound will always hold. So this the derivative of f at a will always be less than your bound of f upon your r times 2 pi for all r smaller than capital R. But we just saw that f is holomorphic on any open ball of radius of center A, regardless of how large the radius is, right? So we can take r to go to infinity, and we can just take say r to be r minus some epsilon, which is like fixed epsilon, which also sends r to infinity, saying that right? So no matter how small or large your delta, you can always bring f prime in. You can always show that for a large enough radius of capital R in small r, f prime will always be less than that delta. By taking this r to go to infinity, which you can do by taking this r to go to infinity. So this thing, because m and 2 pi are obviously fixed, this will go to 0. So this shows that, right? But note, a was arbitrary. We could have taken any other a because our function is holomorphic in the entirety of C, and any radius r for any other a in C. So we say f's derivative is 0 for all a in C, which instantaneously gives us that f is constant. And this finally leads to the proof of the fundamental theorem of algebra. Given f from C to C, non-constant polynomial, there will always exist some z0 in C such that f is C. Okay? And just to prove, right, so we can write f of z to be some k z power k going from 0 to n, and since it's non-constant, we know that there exists some k strictly greater than 0, obviously less than n, such that k non-zero. Right? So automatically we see that f will grow arbitrarily large for z of arbitrarily large modulus, right? You can take z to be something which has a very large modulus and hence show that f of z becomes very large. So writing this concretely, we can show that say, okay, so there exists some r greater than 0 such that if mod z is greater than r, mod f of z must be greater than 1. Right? Okay. Now, for the sake of contradiction, let's assume that f is never 0. That is, for all z in C, f of z is never 0. We can then say, by the continuity of f, that there exists some small r greater than 0, such that 0 is greater than r. Right? Because if for each r you had some zr that grows, that is r grows to 0, you can take r to tend to 0, which would make z tend to 0 because its modulus is bound by, or rather, yeah, in fact, you can take zr, write this down, if not, for all natural numbers, there exists zn such that zn n, right? But we automatically see that this cannot lie, these zns cannot lie in this, mod z greater than r region. So this has to lie in set which, as some of you will come to know, is a compact domain, which means that any function zn or any sequence zn will have some convergent subsequence that converges to some point, right? And by continuity, we can say that at that point, f of say zn converges to some z0, f of z0 must be less than 1 by n for all n, which says that f of z0 is 0, which is obviously a contradiction to what we have assumed. So we have this, that there exists some positive r, so that mod f of z is always greater than r if f never hits 0. So this tells us that 1 upon f of z is always less than r, right? Just by taking the inverse of that, you have that the modulus of 1 upon f of z is always less than r. But we saw that f is never 0. So 1 upon f of z must be a holomorphic function everywhere, right? So this gives us that f, or rather 1 by f from C to C is a bounded holomorphic function on C, which tells us that 1 upon f is constant non-zero because 1 upon f can never be 0 for any real f of z, which tells us that f of z is a constant function, which obviously gives us the required contradiction and concludes the proof that any non-constant polynomial will always be 0 at some point. Yeah, that concludes the proof and hence the talk.
So wonderful talk. So any questions, anyone?
Yeah.
We have like another proof where we take a path so big that it just avoids the origin completely, and then we shrink the domain path that towards some value small, and so the path, the range path continues shrinking until it hits origin at some point.
Right. So that's a proof that requires some kind of algebraic topology to prove very rigorously. So I mean, yeah, there is a very standard proof by algebraic topology and homotopy to show that you'll find it in Moncrief or any standard book. But yeah, I mean, this talk was intended to be expository, elementary, so on and so forth. So I stuck to something that you could discuss in 1.5 hours.
Yeah, any more questions? Okay, if there are none, let's thank the speaker once again.